Okay, so those pictures at the bottom, well, actually, all the pictures on this slide are kind of from the very beginning of my career when I was working in singular optics. Since then, for the last 15 years or so, I've been working more in the dynamical systems of more industrial and biologically motivated problems. And recently, the two have collided to hopefully give us some interesting new pure mathematics, which is very much in development at the moment. So I want to talk around all of that today. So kind of mathematical modeling I'm involved in is an art of approximation of finding differential equation models of different kinds, like the ones at the top here, ODEs, PDEs, difference equations, which describe steady evolution of systems in different ways. And you can think of the mathematical modeling problem, as an art of approximation of this is an abstract way of just writing the thing as successive terms of a Taylor series, but you might instead be looking at trying to build in different biological aspects to a model of different aspects of cell growth and voltage changes, frictional changes in a mechanical model and things. But you start off with your local information. You have at a point, you know what's your function, what your system looks like. And you then can look locally at how the thing changes over time, basically looking at the change of a graph. And if you want to look a bit further away, you need to know how that rate of change is changing, the curvature of this thing. And further, you add more and more to this mix. You can add the next order to try and capture how your system is behaving further and further away. You can think of this blue graph here as graph, not graph, going on and on with more and more waves. And the more of that you want to capture, the more terms you've got to add to that. This is sort of a weak form of modeling. This goes back to the basic calculus you're taught, not even at university, back in high school sometime. If I take a picture like this is a picture of light rippling off a swimming pool. What this kind of thing captures are those, hopefully you can see my cursor here, the sort of dark blue areas in the middle where things are changing nice and smoothly. The really interesting stuff happens at these bright fringes, and it's actually those fringes that organize all the rest of the behavior. And if you can capture those fringes, you can describe the function much better than looking in the nice smooth bits of variation captured by this kind of Taylor series. But those are singularities. In common parlance, those are places where things go wrong, and often they are places where the mathematics breaks down in certain ways. They explain all sorts of things. Hopefully the rendering is good enough for you to see the list on the left there, but elastic buckling, neuron spiking, traffic jams, which I'll show you briefly, cell differentiation, climate tipping points, which I've learnt about from Chris himself. They capture all these kind of things. All of those are a bit difficult for me to show you, so I want to show you a bunch of ones you can see and understand really simply. But essentially, they are just, if I have something like my red graph there, and it starts to change form, so that those turning points come together and eventually annihilate. It seems like a perfectly innocent thing in the function here, but that's a singularity. The topological structure of this graph has changed, and it has massive effects on the system. And it's that simple kind of change that causes things like these bright caustics that you see, and all of this list of phenomena on the left. And it's that we like to study in that we're able to study and gives us lots of nice new pure mathematics. So these singularities are very familiar things to you. You see them all around you. So I wanted to give you some examples of just how and why. The one you probably have heard about is a black hole, but there are much simpler examples all around us. Forgive the hokey animations here. I need a bit of motion on my slides to bring this to life. And I found these slides tucked away from about 10, 15 years ago when I gave a more popular talk I decided they would do for today. So if I have a noise source traveling along, giving out sound waves, then you can picture those as just circles of noise given off by this point as it travels along. And if that source is traveling slower than those sound waves, they just emanate out. They might bunch up a little, giving a Doppler effect. The intensity field around there is just a nice smooth curve that you can easily write down, has a nice Taylor expansion. If that noise source is traveling faster than the waves it's giving out, then it leaves them behind. And as it leaves them behind, they form a caustic. And what you see is on one side of that caustic, I have sound waves. On the other side, I have none. And what that gives you is a zero intensity on one side, which in the geometrical theory jumps to infinity. And on the other side, you have an intensity. And the infinities there, wave effects will tend to soften out because real infinities shouldn't turn up in physics. But they certainly turn up in the geometry and organize all of it. So that is a sonic boom. Something you may have experienced. If you haven't experienced that, there are more familiar examples of exactly the same effect, and one is a rainbow. This was studied back in the 1860s by Airy and Stokes. If we give another hokey animation here, I need a raindrop to explain this one in. As rays from the sun enter a raindrop and bounce through it, they form a similar effect to what we had with the sound waves there. They bunch up along a certain direction, a certain edge, past which there are no ray solutions. So past which there's no light. And if you look in the rainbow picture, you'll see one side. And if you ever look at a rainbow again a bit more carefully, you'll see always on one side of it, it's very dark. And on the other side, it's very light. We can go a bit further, and that's what I'm going to show you in a moment, and see that actually on one side, there should be little ripples in this graph. And you can actually, this is a good enough rainbow picture. If I blow that up, and if the resolution on your screen is good enough, you can see little ripples in that color profile, capturing this Airy function. And you don't have to wait for a sunny, rainy day or a plane flying by at supersonic speeds to see these things. You'll see them, as I said, on rippling swimming pools. It's exactly the same effect that creates those bright streaks. You can see them.
I'm not supposed to sound you. Oh, you're right.
There's some noise coming. If the person could turn off their mic, please.
Okay. So you'll see them if you happen to be sat outside at the moment and the light's good enough, on the reflections on your coffee or your glass. If you're ever unlucky enough to be at dinner with me in a restaurant with nice lighting, I break into a mathematical lecture of that middle picture there of the streaks of light you see coming off a wine glass. They're some of the most beautiful pictures you can see of these caustics, and all of the images I'm going to show on the next slide. So these are showing you actually a beautiful window into higher dimensional mathematics of these optical patterns. And there's an even more common one you will have witnessed, which is a lot more annoying. If you've ever been sat in traffic, so if you write down the formulae for traffic at rest, these come in the form of discrete models, but they turn out to have exactly the same phenomenon. You release that traffic and off it goes. So now maybe you're heading down a motorway. Notice this is an AI generated image in which the AI was not able to understand how cars should quite fit into lanes on a motorway, but never mind. You'll find that you drive along, and as you speed up at some points on the motorway, you'll follow this blue curve, and you will start to bunch up at some points. And as you start to bunch up, you'll bunch up too much, and the geometrical equations would say you bunch up to infinity. Of course, you can't, you'd collide. At some point, you have to slow down and you fall into the oscillations exactly of this Airy function. You start to dip, slow down, everyone spreads out. But then you'll start to enter into, for no good reason at all, another curve where everyone starts to bunch up again, and you'll then spread out again and you bunch up again. And these are called phantom traffic jams. And they've actually measured these on the motorway, and hopefully you're going, oh, I've driven through plenty of these. As you're going down the M5, the M6, the M25, you find that these black lines are vehicle trajectories. You're going along, you seem to enter into a bit of a jam on the motorway, which for no reason releases, but some miles later, it could be a few miles, it could be 10, 15 minutes, they'll bunch up again and release and bunch up again. And you're wondering what accident you're coming up to that's caused them. They can really cause you to stop for minutes on end sometimes. And eventually they just seem to dissipate. And there was never any cause other than the simple mathematics of bunching up cars, and actually the same exact integral that comes out of, at least the integral approximation that comes out of the rainbow, and it's the Airy equation. And it has this form. So it's essentially an oscillatory integral, which has some phase. And those forms of phase take universal forms called the catastrophes, or the elementary singularities. It's not particularly the phi that I'd like to write down here. It's the derivative of that phi, that phase function. They come in the form of a fold, which is just a function that describes a fold in a surface. And that placed into this integral creates that bunching up function of a dark region and then bright dark stripes in the area function. And René Thom in the 1950s and 60s realized these forms came in a whole variety of what he called the elementary catastrophes, a set of well-defined shapes. The cusp, the swallowtail, you can see each of these basically are just a polynomial of successively higher orders. They gave them very nice names, described by the forms of the surfaces in parameter space that they have. As you get into umbilics in 2 dimensions, you can have multiple cases, and this thing goes on. They're actually related to the ADE classes, symmetry classes that were mentioned earlier. I better not get into connections with the earlier talks because I could speak for a whole hour about those. And these integrals give you universal optical patterns. So these are calculated numerically from those integrals associated with those. So near those shapes, if you like, in a surface, when light's refracting off them, you will always have these universal forms in their reflection in their intensity profiles. So from these elementary singularities, you have these elementary integral patterns, and whenever these are very hard to calculate, they're multidimensional, very highly oscillatory integrals. Whenever someone comes along with a new computational technique, or when someone tells me I should be using Python to do all my simulation these days, or I should be using Julia, I like to test these things out on these integrals because they're so challenging usually for computers. When I was trying to generate these recently, I had trouble with my usual bit of software, so I jumped into AI and spent a very illuminating day having conversations with Microsoft Copilot and with ChatGPT, trying to generate these pictures. It was able to use some very clever techniques, but this is all it could do. You can see the fold, it did pretty well. The cusp, okay. The swallowtail's getting a bit bad. The butterfly, it's really struggling. And the umbilics, actually, the first umbilic, it did okay. The second one, it's really quite terrible. I sort of throw those out there to be a little bit provocative, to say that the geometrical understanding of these is such that I find AI struggles still rather with this kind of mathematics, and I find that reassuring. But I'm sure people will develop suitable AI techniques to deal with those in the future. And back in the 80s, people were able to produce wonderful images of this, verifying that these predictions of Thom really turn up exactly in optics. But not really outside optics or fundamental physics. Outside of that, these singularities, these catastrophes, struggled to find non-controversial applications. They were applied in many places, but not too well. The nice thing about these is they take some really old mathematics, Laplace method, if you've heard of it, steepest descents, knitted all together in just stationary phase methods to understand integrals through these catastrophes, these simple local singularities, and bring it into this integral theory and show that they create uniform types of images, patterns around these singularities, what we call uniform asymptotic smoothing. And then I want to mention, I haven't really gone into the detail of the singularity theory. It has to do with germs and ideals. But within Thom's method, there's this wonderful Thom Boardman procedure that classifies any possible singularity of a simple function and mapping. That's just the equations involved. They involve derivatives of a function. The big F there is the same as the little f over on the left. Derivatives of the function and its minors and so on. Let me just show you the numbers involved in doing those calculations to identify what these singularities are, these catastrophes. So if I have a system of 4 dimensions with 4 parameters, so the parameters are the A, B, C, D appearing in these, as we had recently in a problem we were studying, it would take you 95 million calculations. You'd have to write down 95 million equations to identify that singularity. Now, there's no system in biology or physics, except somewhere in some Marvel multiverse, that can satisfy that number of equations. I'm going to try and fix that in a moment, or at least tell you how we fix that with a bit of new pure mathematics. Now, the other problem is those functions, that singularity theory applies just to mappings. There's all sorts of physics it doesn't really apply to. It can be applied to gradient fields, as René Thom did with his catastrophes, but it can't be applied to most of the real world physics, engineering, and biology that we want to apply it to. But recently, colleagues came to me with what they thought was a swallowtail or a butterfly catastrophe in a biological model. So the biological model is the one shown above, slightly simplified. It's a partial differential equation, a reaction diffusion. It describes cell potentials in biological growth. And they saw these patterns in some bifurcation diagrams. I won't go into this in detail, but they saw patterns in their bifurcation analysis, their stability analysis, that seem to show the kind of shapes you see in catastrophe theory. These are some slightly better ones pulled out of it. Take that middle one, and then I'll just rescale a little bit so you can see more clearly. That shape that you have there is exactly the shape on the right. It is actually a butterfly. But according to all the theory that's been around now for 50, 60, 70 years, there's no reason to see that in this kind of partial differential equation context, in these biological models. So we had a problem. I needed to explain why these things were there, dug through all the literature, found to my surprise there was no good way to explain these. There was definitely no way to detect them, to provide equations to verify what they were. So I applied bits and pieces of geometry I'd picked up over the last 20 years, and really with the back of the envelope calculation showed that they were in fact definitely butterflies. And that actually, with what we found, it seems that as you move around in these kind of bifurcation spaces, you can explain the sort of patterns that come out of, well, you can explain changes in patterns that come out of these kind of partial differential equations. I'm just dropping that in there for anyone who studies Turing patterns at all as a little, again, to be a little provocative about the potential interest of these things. I don't have time to go into that one at the moment. But this little geometrical argument we came up with took that number of conditions, which were many, many millions, and through something called an underlying catastrophe, basically we posited that any system, no matter what it looks like, if it is forms of differential equations, has underlying it one of Thom's most simple catastrophes. And the geometrical arguments reduced all of this to just the most elementary number of conditions, the minimum possible number of conditions you could have. So I'll speed through this one pretty quickly, but it gives us a new understanding basically of Taylor series, that the interest in Taylor series isn't just what these different terms look like, but it's about where they vanish. If I have an equilibrium, I know the next term has a trace and determinant that explains it, that describes its stability. But if those vanish, then I get the next singularity. And then I get new invariants that we didn't know about before that describe the next order of behavior. And when those vanish, I get cusps and so on. And there's a whole new set of invariants that we're discovering of these Taylor series associated with these singularities where successive things vanish. So from all of these different areas of physics, we develop all of these universal patterns and shapes and form that appear, and they seem to be pointing to a new understanding of something as elementary as a Taylor series. And what we're still developing is this new element to singularity theory that reduces all these calculations to very simple geometrical understanding of these objects. Thank you.